Hello and welcome to a new video. This is for Unit 9, Graphing Quadratic Functions of my own personal Algebra 1 curriculum that I've been developing this year. This is Lesson 1, so we're going to start kind of in on this new journey, which is talking about graphing quadratic functions. So we've been solving quadratic equations. The difference between an equation and a function typically is just that an equation would only, the equations we've been solving have only had one variable because then we can solve for that one variable. They've only had x, not x and y. Whereas a function, you would typically have x and y, or you could have f of x, the f parentheses x instead of y. That would just be notation, right? But that's the difference kind of between what we're doing. We were solving the equations, which has its purpose, believe it or not. And now we're going to talk about graphing quadratic equations, quadratic functions. We're going to start off with the simplest possible quadratic functions that we can, which are quadratic monomials. Try saying that 3 times fast. Quadratic monomials, quadratic monomials, quadratic... I thought I was going to make it, but then I didn't. So seriously, try it. Okay, so let's take a look here at what's going on. So first off, what is a quadratic monomial, just to make sure that we're on the same page? Quadratic means that our largest exponent is 2. So the highest thing we can have with x is an x squared. We can't have an x cubed or an x to the 4th or anything like that. It could have an x involved in it if it's quadratic, but we also have to have an x squared. A monomial has one term, because remember the prefix mono means one, like monotone or monotony, which those are really similar words. Anyway, some examples of some quadratic monomials would be things like x squared, or 5x squared, or negative 3x squared. We could use other letters, by the way, but basically this idea that there's only one thing. Each of these this is 3 separate examples because these are 3 separate kind of one-term quadratic things. So that's what we're going to be graphing today. And in math, when we approach something and we don't know how to graph it, we don't know what it looks like, we start off by using a table of values. So that's what we're going to do. And when we're doing a table of values, one of the trickiest things can be knowing what to pick to plug in for x. So the best thing to do is to start with 0 or around 0, because those numbers are going to be the easiest ones to plug in, most likely. Whereas if we pick like numbers farther away, not only will the math maybe be harder, but it's less likely to fit on a nice coordinate plane. So I'm going to graph y equals x squared here, which means that essentially with my table of values, I'm just taking whatever x is and timesing it together times itself. So squaring it and then getting an answer. So if I start with 0, because even though this is in order from -2 to 2, what I would really do if I was approaching this personally is I would say, well, 0 is the easiest number to plug in most of the time. So I'm going to do 0 squared and get 0 and then work out from there. So like 1 squared is 1, but -1 when we square it, and we have talked about this at some point before, right? But -1, when you square it, you're saying -1 times -1, which is a positive 1, and that's important. It's kind of a big deal that squaring negative numbers makes them positive. 2 squared would be 4, but also -2 squared would be 4. So if I graph these points, and way back in Unit 2, if you've been with me since then, we did graphing by a table of values before we started graphing lines, and we graphed some that had x squared, so you may remember what it looks like from that. We're going to graph -2, 4, -2, 1, -1, 1, 0, 0, 1, 1, 2, 4, and go up and to the right and make an arrow at the end to show it goes up forever. Because I only stopped my table of values out of laziness or efficiency. Let's go with efficiency, because we could totally fit 3 on this graph I have, because 3 squared is 9 and -3 squared is 9. And you can go farther than that and know what the answers are. So we know it does keep going up and up and up. The bigger the number you plug in, the bigger the number you'll get. But I would say that for things like this, graphing about 5 points is probably good enough. Now, some things about this graph. This is called a parabola. And that, I guess, kind of refers to, I mean, I've only ever heard it referred to as with equations that have an x squared in it. So it does have to do with what our equation is, that this is quadratic, but it also kind of has to do with the shape of what we have. This is parabolic, if you want a fun word to try to use. One of the things you may notice about this is it kind of looks like a U, or maybe kind of like a V, but it's supposed to be curved at the bottom, not pointed at the bottom. And so this is a U-shaped graph, and this pattern that we have of that we're squaring each of these numbers is going to end up being important to us. But that's kind of the idea here. This is a parabola. A couple of vocabulary things, actually, before I move on, is that parabolas have what's called a vertex, and that's a word that you should have heard in math before, maybe a few different times. You may have heard the plural of vertex more often, which is vertices. When we talk about three-dimensional figures, the corners of three-dimensional figures are called vertices. In algebra and beyond, when we talk about a vertex or vertices, we typically are talking about a highest or lowest point, or kind of a most important point is another way I like to think of it. So the vertex of this particular parabola is this down here at the bottom, 0, 0. Call that the vertex of this. The other thing that parabolas have going for them is what's called an axis of symmetry. So if you look at this graph, and if you draw badly, I get it, but you can kind of tell, right, that you could fold this graph in half and it would look the same, like on either side if you fold it this way. So there's this kind of imaginary line here that is called the axis of symmetry that is really helpful, because once we start being confident about plugging in numbers, if you notice, right, that the middle point, the vertex was 0, 0, and then these two are both 1, and these two are both 4. That's because we have symmetry happening. So one of the ways to graph parabolas in general is to find the vertex, then find a couple points on one side, and then use symmetry to help you finish it out. So the axis of symmetry here is a vertical line that goes through 0. So it has an equation actually of x equals 0. So that's just kind of some notes. Another thing that we maybe look at with parabolas is which direction is it opening. So this is opening up because this part is the opening and it's up. And so as we kind of go through this lesson and the next, we might try to think about, like, what are the things I actually can know without having looked at the graph, and what are the things that I actually need to graph it to be able to see where it is. So let's look at some more examples. These are all quadratic monomials. So we're actually going to notice that really limits what's going to happen to these parabolas. We're going to do more in the next lesson. So that's cool. This one says y equals 2x squared. So what's happening here is we're actually doing 2 times x squared, just to make sure we understand that. And so PEMDAS, order of operations, says you should do the exponent first and then multiply by the number. So I'm going to take these numbers and square them and then times them by 2. So let's do that with 0. 0 squared is 0 times 2 is still 0. So that point did not move. Let's do that with positive 1. So 1 squared is 1 times 2 is 2. Now, I want to point out that if you do it incorrectly, if you say 2 times 1 is 2 and then you square it, you get 4. That's not the right way to do it. We have to square it first and then we multiply. Then if we do that with 2, we've got 2 squared is 4. 4 times 2 is 8. Now, if we are confident that 0, 0 is the vertex, which it is, but I don't know that you've got enough information going for you to be sure of that, we would then be able to say, okay, the other direction follows a pattern. Should have 2 and then 8. I do think it's worth still checking on this since we are new to this whole thing and making sure you understand why it ends up being 2 and 8. We're going to square -1, which is +1. -1 times -1 is +1. Then times it by 2, so this is 2. Then 2 times -2 squared, so -2 squared is +4. +4 times 2 is 8. You may notice if you look back at example 1 and then look at this one, that essentially this is just all of our y values multiplied by 2. And if you're like, I wonder if that's like a legit thing or if that's a coincidence that 2 is right there. It is definitely not just a coincidence. It is like a legit thing that 2 in front of x squared is actually taking our graph and it's making it stretch its y values up so that they're going to be twice as far as they would have been without the 2 there. And I say that because that as we learn more and more things about graphing, it's helpful to be able to understand what the numbers in the equation are actually doing. So I'm going to graph this 0, 0, 1, 2, 2, 8, -1, 2, -2, 8. And see how this is like a narrower sort of shape than the last one was? So what we've done is we have essentially pulled the points in horizontally, but the math we actually did was we said, let me take those y values and just move them farther away from the x-axis, move them farther up. We actually call this a vertical stretch. Vertical because it's up and down, stretch because we made the points farther away from the x-axis. So that's how that works. Let's look at the next example. This one says y equals -x squared. This is where it really gets a lot of people tripped up on order of operations here. So let's start with -0 squared. We square first. 0 squared is 0, and there's a negative front, so it's -0, but 0 is not really negative, so it stays negative. -1 squared. Now you may be thinking, you can't trick me. I know -1 squared is really +1. But wait, what are we actually squaring here if we're plugging 1 into -x squared? What we're really doing here is we're saying, let me fill in this spot here. So I'm going to fill it in with 1, which means I need to square the 1, and then I've got a negative in front of that 1 that's going to change the sign after I square it. Okay? So this is a -1. You follow? If I do it with now plugging in -1. So I put -1 in that spot and I look at my order of operations. If it helps to think of it this way, think of it like it's a -1 in front of x and that we're just lazy mathematicians that didn't want to write -1x squared, which is absolutely true. We're just being lazy, not writing the 1 in front. So if I write it this way, it might be easier. We're doing -1 times -1 squared. So we square -1 and we get +1, and then we times that by -1 and get back to -1. I know that it's not the easiest thing in the world, so it takes some getting used to, and this is something that definitely students struggle with, like, very often. All right, 2. So I'm going to square 2 and get 4, times it by -1 and get -4. I'm going to square -2 and get +4, times by -1 and get -4. You may notice if you look back, not at example 2, but at example 1, if we compare this to y equals x squared, what the -1 in front of x squared does is it makes the y values just negative. That's all it changes, which if you think about it, hopefully that makes sense, that that's what would happen. When I graph this, what it does is it turns my parabola upside down. Like so. So otherwise, it's the exact same shape or size, if you want to think of it that way. It's just that it's been reflected, is the fancy math word we use for it. It's been flipped, to use a less fancy word. It's been flipped over the x-axis. It's been reflected over the x-axis. So this is a reflection. Okay, let's look at our last example, which is y equals 1/2 x squared. Now, I know that in general, people tend not to like whenever fractions are involved, and I get it. So let's just go through and get it done together and see what happens here. By the way, you do not have to stick with this -2, -1, 0, 1, and 2. I'm going to go ahead and stick with it, but maybe add a couple more points. And so if you realize because you have a fraction that there's something that would be better to plug in than these points, then, I mean, that's totally up to you. You can do that if you'd like to. So I'm going to plug in 0. 0 squared is still 0. 0 times 1/2 is 0. Then I'm going to plug in 1. 1 squared is 1. And 1 times 1/2 is 1/2. And that basically because I knew it was going to be relatively simple, that's why I left it as 1. If it was something more complicated than that I felt like would be hard to work out or hard to imagine where it's at, then I would actually skip 1 and go to 2. Because when I do 2, 2 squared is 4, and 4 times 1/2 is 2. 4, knowing that like because it's 1/2, I need things that are even, that it's going to make it more likely that I will have something that works out evenly, is super helpful. So now I'm going to do -1. So -1 squared is +1 times 1/2 is 1/2, and then -2. So -2 squared is 4. 4 times 1/2 is 2. So at -2, we're only at 2. At -1, we're only at 1/2. Then 0, then 1/2, and then 2. I feel like it's worth mentioning, like 3 would not be fun to do, but if I plugged in like 4 just to get an idea of kind of what it's looking like as I go along, I'd do 4 squared is 16. 16 times 1/2 is 8. So at 4, it'd be 8. Because I feel like I would just like completely not draw this accurately, which is fine if I hadn't found this kind of extra point. And notice I can use symmetry to know that -4, 8 is also a point. So this is what that looks like. If you can compare this to the very first example, what this should look like is, honestly, you probably look at this and think it looks wider. So whereas example 2 looked narrower, this one looks wider. And what's happening with that is that it looks wider because we've actually taken all the y values and we've moved them closer to the x-axis. So that 1/2, it took all of our y values and times them by 1/2 and made them all smaller. So this is called a vertical shrink, or I have had a textbook that I taught from that used the word compression instead. There's this idea that vertically we're taking our graph and we're bringing things down so that they're closer to the x-axis. That's what's happening here. So we're going to do some practice on this for this lesson of just kind of getting the hang of plugging in things. And then in lesson 2, we'll start graphing things that are a little bit more complicated. So that'll be fun. As always, thanks for watching. I hope you have a great day, a great time graphing these. And leave me a thumbs up because you like me, or you liked the video, or you're like, hey, parabola is a cool word. I'll give it a like for that. And yeah, thanks for watching. Bye.